Hello student, today we are going to start our new topic from the class 11, that is waves. Over here we will study what is waves. Waves is basically, it is disturbances which travel from one point to another in which particle of medium are vibrating about their mean position. See, we will study about different type of waves. That is, first we will go for mechanical waves. What is that? Mechanical waves. We say that these are those waves which require material medium for its propagation. Examples are, first, that is water waves, sound waves, and seismic wave. That wave which is transmitted during earthquake, seismic waves. Then we go for electromagnetic waves. What is that? We have electromagnetic waves. We say that these are those waves which do not require any medium for its transfer. These are those waves which do not require material medium for its propagation. Examples are light wave, UV ray, infrared, X-ray, all are basically electromagnetic waves. Then we have matter wave. What is that? Matter wave, basically it is associated with microscopic particle such as electron and proton. These are the waves associated with the electron and proton. What we have learned? Wave is basically disturbances which in which it travels from one point to another in which particle of the medium are vibrating about their mean position. Then we have mechanical wave. It require material medium for its propagation. Then we have electromagnetic waves. It does not require any material medium for its propagation. It has basically two components. Why it is called electromagnetic wave? It has two components, electric and magnetic field, which are perpendicular to each other. And then examples are light wave, UV ray, infrared, X-ray and all. Then we have matter wave. It is wave associated with the microscopic particle. See, what are the conditions necessary for transfer of waves, mechanical waves? Means necessary condition for transfer of mechanical waves. Means what are the necessary condition? We require, means substance should have, like, through which mechanical wave is being transferred, it should have elasticity. Elasticity means it is property, the material medium should have elasticity so that it returns to original position after being disturbed. Then we have, it should have inertia. A body should have inertia so that it can store energy. Then there should be less friction between particles. There should be less friction between particles so that less energy is lost during transmission. Now we'll see that these are the basically condition necessary for a transfer of mechanical wave. The body should have elasticity so that it returns back to the original position after being disturbed. Then we have, the body should have inertia so that it can store energy. Then we have less friction between particle. What is that? So that less energy is lost. Basically less friction between particles. So there is less energy loss during the transmission of waves. See, when we talk about waves, basically we'll see that it will have equation like this: y is equal to a sine omega t minus kx. Over here, this is the y is what? This is displacement. A is what? This is amplitude. What is that? It is maximum displacement of the particle from the mean position. Then we have omega, angular velocity, which can be written as 2 pi by t or 2 pi into nu. And then we have k. K is basically angular wave number, that is equivalent to 2 pi by lambda. When we have like, it is given like minus kx, means the wave is moving forward in a positive x direction. When we have like positive kx, then it is returning back. See, we'll see that what happens when the wave is being transferred. Let us suppose the wave pulse is given like this, and what happens when it gets reflected back from the rigid boundary. See, what we'll see that? We'll see that if it is a rigid boundary, what will happen? The wave will return like this. And in that case, equation will be what? There will be phase difference of 180 degree minus A, and this is what? Sine omega t plus kx. Then we have like, suppose it is open boundary. In that case, what will happen? This is what? Rigid boundary, and when the wave is being transferred and it passes through open boundary. This is basically open boundary where it can like move. In that case, what happens? the wave was written like this, and there is only phase difference. A sine omega t plus kx when there is open boundary. See, what we'll do is that we'll go for superposition of waves, and what will it result to? See, what is basically we'll talk about what is standing waves or a stationary wave. What is that? A stationary wave or standing wave. We say that if two wave trains have same frequency, same wavelength, same amplitude, but they move in opposite direction, then what will happen? We'll get a standing wave. Suppose this is wave, and there is another wave which is moving in opposite direction. The resultant will be this. This is basically the standing wave. Means we can draw like this. These are the wave, and this is moving in a positive x direction. Then there is wave which is moving in the opposite direction. Then when they superimpose, they will form a stationary wave. When they will form the stationary wave, if they have same frequency, same amplitude, same phase, but they are moving in a opposite direction, then they will form a stationary wave. Then what we'll do is that we'll go for finding condition for obtaining maxima and minima in the case of standing waves. See, this is what we have, like y is equal to a sine omega t minus kx. Then we have another wave. This is what? Reflection from the rigid boundary. In this case, what will happen? Y is if y is basically what? Sine omega t minus kx minus a sine omega t plus kx. This is the case for the reflection from the rigid boundary. See, what will happen? Sin c minus sin t is what? 2a cos omega t into sin c minus d by 2. It is coming out to be this. This is what? Minus 2a sin kx into cos omega t. See, we know that suppose the boundary is fixed, whatever might be the value of the waves, what is the value of the waves? Would you see that this is we have certain disturbances there. This is what? K into x. See, when the value is, this is L, see what you get? Y is basically sine k into x, and we know whatever might be the value, but it is going to be 0. In this case, what we are getting? This is n pi. K, this is x is L, this is what? N pi. K is what? 2 pi by lambda into L into n pi. See what will happen? This is pi and pi get cancelled out. What we are getting? Lambda is equal to 2L by n. See, in the case of a stationary wave, in the case of a stretched string, what is that? We will get normal standing waves in the case of a stretched string. This is the case of stretched string. This is normal mode of vibration or we say that it is a fundamental frequency. See what we have in the whole length. This is what? This is the length L. We will see we have got the formula like this. Lambda is equal to 2L by n. So what we see that it is 2L by n. When n is equal to 1, what do we get? In whole length, what we are getting? Half wavelength. So what happens? We get wave like this. And we know that velocity of sound in a stretched string is what? That is equal to T by M. T is what? Tension on the string, and M is mass per unit length. T is what? Tension on a string, and M is what? Mass per unit length. So what we are getting? We have to find frequency. Then velocity is what? Frequency into wavelength into root over T by M. What we are getting? Nu 1 is 1 by lambda 1 into root over T by M. So what we have lambda? Lambda 1 is equivalent to 2L. So we can write 1 by 2L root over T by M. Next, what we have? We'll calculate the second normal mode of vibration. We'll go for second normal mode of vibration. In that case, second normal mode of vibration, or we say that it is first overtone. So what will happen? We have like lambda is equal to what? 2L by n. In second normal mode of vibration, what we have? N is equal to 2, means what? 2L by 2, it is coming out to be in a whole length. What we are getting? A complete wavelength. So what we have? This is velocity is what? It is equal to root over T by M. Tension upon mass per unit length. When we are going for the frequency part, it will come out to be what? T by M, and nu 2 is basically 1 upon lambda 2. Lambda 2 is equivalent to L. So this is L root over T by M. Now we go for third normal mode of vibration, or first overtone. Third normal mode of vibration, or second overtone. See what we get? This is our lambda is what? 2L by n. What we have for third normal mode of vibration or second overtone? What we have? This is lambda is equal to 2L by 3. In whole length, what we have? 1.5 wavelength. Means what? It is like this. 1.5 wavelength. Then what we have? We go for the velocity is our V is equal to root over T by M. Then comes frequency. Then there is wavelength into root over T by M. What we get? Nu 3 is what? 1 upon lambda 3. Lambda 3 is what? 2L by 3 into root over T by M. So we are getting first, second and third normal mode vibration in the stretched string. Now we'll go into calculating normal mode vibration in the open and closed organ pipe. See, in the case of open organ pipe, what we have? We have first normal mode of vibration will be like this. Means what? in whole length, what we are having? A half wavelength. This is the case of open organ pipe. What we are calculating? First normal mode of vibration or fundamental frequency. First normal mode of vibration or fundamental frequency. So see what we are getting. We know that velocity of sound in air is what? V is equal to root over gamma p by rho, where gamma is like ratio of Cp upon Cv, and P is the pressure of the atmospheric pressure, rho is the density of the gas. So this is what? This is frequency into wavelength is equal to root over gamma p by rho. So what we have? This is nu one is what? In the case of first, lambda 1 will be equivalent to what? 2L. So what we get? This is 1 by 2L root over gamma p by rho. Then we'll go for the second normal mode of vibration or first overtone. Second normal mode of vibration or first overtone. See what we get? This is velocity is basically root over gamma p by rho. Velocity, this is frequency into wavelength into root over gamma p by rho. Then we have like in whole wavelength, second normal mode of vibration will have like this full wavelength. Means in whole length we have lambda. In that case, what will happen? This is lambda L root over gamma p by rho. Then we have third normal mode of vibration. Third normal mode of vibration, or we say that it is second overtone. How to get this? This is velocity is what? Root over gamma p by rho. And third normal mode of vibration, what do we have? The waves are like this. It is coming out to be a 1.5 wavelength. In whole length, what we have? 1.5 wavelength. See what we'll do? Nu 3 into lambda 3. This is what? Root over gamma p by rho. What we are getting? Nu 3 is basically 1 by lambda is what? Lambda will be equivalent to L. This is 3, this is 2. Lambda will be 2L. This is 3 root over gamma p by rho. This is the case of the open organ pipe. Now we'll go for closed organ pipe. We'll go for the normal mode vibration of fundamental frequency in the case of closed organ pipe. In case of, see what we have, in case of closed organ pipe, what we have? In full wavelength, full length, we'll have 1 by 4th wavelength. Normal mode of vibration, normal mode of vibration in closed organ pipe. See what we have. In whole length, what we are getting? Whole length, only quarter of the wavelength is there. We have the formula. Velocity is basically velocity of sound. This is gamma p by rho. This is nu 1. This is lambda 1. This is gamma p by rho. This is nu 1. This is 1 by lambda. This is gamma p by rho. and lambda 1 is coming out to be what? This is 4L. So what we are getting? Nu 1 is what? 1 upon 4L root over gamma p by rho. Next we come to second normal mode of vibration. Second normal mode of vibration. Now you see that it is what? Nu 2 will be equivalent to 1 by lambda 2 into root over gamma p by rho. So second normal mode vibration, what we have? See, it is like this. Means whole length what we are having? 3 by 4th wavelength. So what we have? Lambda will be equivalent to 4L by 3. This is 4L, this is 3, this is root over gamma p by rho. Then we have third normal mode of vibration. What we have? In third normal mode vibration, the starting point is going to be 0. What do we have? Means quarter wavelength. Means 1.25 wavelength. In full length, what we are having? 1.25 wavelength. Means we have like lambda will be equivalent to what? 5 by 4 lambda, or lambda is what? 4L by 5. What we do is, we know that frequency third is what? Lambda 3 into gamma p by rho. Nu 3 is coming out to be what? This is lambda 3, this is 4L by 5 root over gamma p by rho. These are the waves in the case of open organ pipe. Now we'll move on to Newton's formula of velocity of sound. How Newton was able to find the velocity of sound. What was that? See what we have. This is Newton's formula of velocity of sound. See, in this case, what do we have? According to Newton, the velocity of sound in air is basically isothermal process. And isothermal process, we know that it is PV is equal to constant. Suppose we find the derivative of it, it is coming out to be this. We have like minus V delta P by delta V. This is equivalent to what? The bulk modulus also. Bulk modulus, we know that it is basically pressure upon delta V upon P, which is quite similar to this. So what we are actually getting is velocity of sound in air is basically pressure upon density of gas. This is what? Atmospheric pressure, and this is what? Density. Atmospheric pressure is what? It is equivalent to 1.01 into 10 to the power 5. And we have density of gas or air is what? 1.3. Suppose we place this value over here, 1.01 into 10 to the power 5 divided by 1.3, it is coming out to be what? 280 meter per second. This is the velocity of sound in air. But practically we found that it was much greater than this. It was coming out to be like 330 meter per second. But over here Newton was able to get only 280 meter per second. But it was corrected by Laplace, who said that velocity of sound in air is a adiabatic process. That is basically Laplace correction. What is that? Laplace correction See, in Laplace correction, what he did was that he said the velocity of sound in air is a adiabatic process. Velocity of sound is what? K adiabatic upon my density of air. But we know that in the case of adiabatic, we have formula VV gamma is constant. So when we find derivative of it, it is coming out to be gamma minus 1. This is delta V. This is V to power gamma. This is delta P is equal to 0. See, when we take this out, it is coming out to be delta V. This is what? V to power gamma minus 1 into delta V. It is coming out to be delta P V delta V. So what we got that? Gamma into P. Gamma is basically the ratio of Cp upon Cv. Specific heat capacity at constant pressure to the specific heat capacity at constant volume. So what he was able to get is gamma P by rho. Value of gamma is basically 1.4 for air. So what we have, when we place this value out over here, it is coming out to be, this is atmospheric pressure 10 to the power 5 and this is 1.3. He was able to get 332.3 meter per second. This is basically approx. Means the correction from the Laplace was that the velocity of sound is, he was able to get the exact values. Now we'll study about what are the factors which affect the velocity of sound. Factor affecting velocity of sound. See what we have. Velocity, what we got? Velocity is what? Gamma P by rho. Over here, what we see that P V is basically constant. This is what? Volume is what? Density is basically mass upon volume. Volume is mass upon density. So we see that mass is not going to be changed. So P by rho is going to be constant. So we see that velocity of sound is independent of pressure. Velocity of sound is independent of pressure. Then we have velocity factor dependence on the density. We see that velocity of sound is inversely proportional to the root of density. Means velocity is inversely. So let us compare to this. Suppose we calculate the velocity of hydrogen to the velocity of oxygen. We'll be able to see that, you know, the density of this is 1 and this is 16. The velocity of hydrogen will be 4 times that of oxygen. First we'll go for the velocity of sound in humid air and in dry air. What is that? We know that density of dry air is greater than density of humid air, and we know the velocity is inversely proportional. So what we have? Velocity in a humid air is greater than velocity in dry air. Then we come to the point like what is the how temperature affect the velocity of sound in air. Effect of temperature. Effect of temperature on the velocity of sound. We know that V is what? Gamma P by rho. We know that PV is equal to nRT. We see that velocity is like directly proportional to the temperature. Suppose we want to go for exact value as to what the variation are. We'll see that Vt is what? It is, we'll convert into the Kelvin. Suppose it is 0, we have like 0 plus 273. Suppose we go for the calculation part, it is coming out to be what? This is 1, this is 273 by 273, 1. This is t upon 273. What we do is that it is in root. Now we'll go for the binomial part. It is coming out to be 1 plus t upon 546. See, suppose we go for like, this is what Vt, this is V0, this is 1, this is t upon 546. See, it is coming out to be what? This is what? Vt, V0 minus 1, this is t upon 546. This is Vt minus V0 upon V0, t upon 546. See what we have? This is, we can find the values. Vt minus V0 upon t will be equivalent to V0 upon 546. We know the velocity of sound. It is coming out to be like 340 something. This is what? 546. So this is coming out to be 0.61. We see that velocity of sound increases or decreases by 0.61 meter per second for each degree rise or fall in temperature. This is the relation between the velocity of sound and the temperature part. Then we have like, what is Doppler effect? What is Doppler effect? See, we say that, let us suppose there is source of sound. There is basically, this is the listener. What happens? Suppose source is moving toward the listener and listener is moving away from the source. Basically, what is Doppler effect? Basically, Doppler, it says that there is alternate variation in the frequency of sound when there is apparent change in the frequency of sound when there is a relative motion between the source and the listener. And the formula is, nu dash is what? V minus VL upon V minus Vs into nu. Over here, this is what? Apparent change in the frequency. Apparent change in frequency. This is what? Frequency of the sound. V is the velocity of sound. It will be 340. VL is what? Velocity of listener. Then we have Vs. This is what? The velocity of the source. And various formulas related to it can be derived using this. Let us suppose we can have a case in which source and a listener are moving toward each other. In that case, what will happen? Nu dash will be what? It is V. See, listener is moving in opposite direction. This is, it will become VL. This is V minus Vs into nu. When the source and listener are moving toward each other. Suppose if the source and listener are moving away from each other, in that case, source is moving, deviating. So what will happen? And listener is going toward its own way. So it will become like this. Clear? There are loads of cases which can easily be found by using simple technique. That's all for today. We'll meet in the next class. Thank you.